All right, let's kick off section 6.3 here. We are going to talk about definite integrals and antiderivatives. So we've been talking about antiderivatives for a while now. The book just introduces the concept more or less here. At this point, they do bring it up a little bit earlier on, but not explicitly calling it antiderivatives. Anyway, we've already talked about antiderivatives, so we won't spend a lot of time on the rules for antideriving. Specifically. So you'll see that in the book if you go through the chat or through the section, but we won't spend a lot of time there. Let's talk about rules for definite integrals, because there's some patterns in definite integrals that are worth sort of learning and remembering. All right, so the first rule that we're going to talk about, let's zoom in here a little. The first rule that we're going to talk about, we'll call it rule number 1, is this, which is if you have the integral from b to a of f of x dx. Now, b to a, in this case, a is always less than b. Okay, so in our example here, a is less than b. That is, a is to the left of b. So you can see that our bounds are the reverse of what they were when we defined what a definite integral was. This is going to be equal to the negative of the bounds in the correct order. All right, so the negative of the integral from a to b of f of x dx. And you can sort of think about this graphically. So if this was our shaded region from a to b, if you wanted to go from b to a, then our delta x, if you remember back from the proof, our delta x would be in the negative direction because we'd be going this way as we computed the rectangles. Okay, so if you wanted to do that, you'd have to take the negative of the entire integral going the correct way. All right. So, and there are other ways that we could visualize that, but that's rule number 1. Number 2 is the simplest of all integrals, or the family of the simplest of all integrals. If you have the integral from a to a of f of x dx, that integral is just 0 because the upper and lower bound is the same. There's actually no area there, so hopefully that one is fairly intuitive or easy to believe. The next one, the integral from a to b of some constant k times f of x dx. All right. Now, this one is equivalent to when we did the exploration, or when you did the exploration, there was a question. We gave you the value for the integral from 0 to pi of sine of x. And then one of the questions was, what about from 0 to pi of 2 sine of x? And what that turned out to be was 2 times the area that you were given. It ended up being double the area. So the rule here, the constant rule, is that you can take the constant out in front of the integral. So k times the integral from a to b of f of x dx. Okay, so in our example from the exploration, f of x was sine, and so the 2 we could just take out in front of the integral and just multiply it by the thing that we knew. And you did that without knowing the rule, but there's a rule that that kind of underpins all of those types of integrals. All right, so you can take the constant out in front of the integral. All right, so rule number 4 is the sum and difference rule. Had some technical glitches there, so I've already got this written down. It's the integral from a to b of a function f plus or minus a function g, and that can be rewritten in this way: the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Okay, so you can split the integral up into 2 parts and add or subtract accordingly. Rule number 5 is additivity. All right, and the additivity rule says this: if you have the integral from a to b of f of x dx plus the integral from b to c, notice that the b is the same here, of f of x dx, then the result is simply the integral from a to c of f of x dx. So the integral from a to c f of x dx. All right, so that's the additivity rule. You can see this graphically pretty easily. So if I have some curve here, let's put A right here, B right here, and C right here. B has to be the same number, right? I mean, by definition, here, B is the same value, right? So you do have to have this feature of this area exactly lining up with this area. And so instead of summing the two areas, you can just integrate from A to C. Okay. Or if you were integrating from A to C, you could just sum the areas. It works the other way as well. All right, rule number 6. Domination. Domination is rule number 6. And here's what this looks like. If f of x is greater than or equal to g of x for the entire interval a to b, so on a, b, including a and b, then we can say the following. So we say if this, then this. So then the integral from a to b of f of x has to be greater than or equal to a to b g of x dx. And here's another one that you shouldn't just take my word for it. We can sort of visualize it. So what this says is if I have two curves f and g, so f, and on the interval from a to b, f of x is always above g of x. Well, when you go to take that area then, the area of f here in this pink salmon color or whatever will have to be greater than the area or equal to the area underneath of g. Okay, so those are the 6 rules that we're going to kind of formally use here, and let's apply them. So let's do some examples. So suppose the following. Suppose we have the integral from -1 to 1 of f of x dx is equal to 5. We have the integral from 1 to 4 of f of x dx is equal to -2. And then we also have the integral from -1 to 1 of h of x dx is equal to 7. Okay, so we know these 3 things, and I want you to answer the following questions. Okay, you should pause the video, try it, try these problems, and then see how you do. So we'll start with the integral from 4 to 1 of f of x dx. Then we'll take the integral from, let's actually go across here. So then we'll take the integral from -1 to 4 f of x dx. And then we'll take the integral from -1 to 1. Oh, no, I'm going to go below for this one. So, so C is the integral from -1 to 1 of, okay, we got to be careful here, 2 f of x plus 3 h of x dx. And D is the integral from 0 to 1 of f of x dx. E, and this is the last one, the integral from -1 to 4 of f of x plus g of x, or h of x, all with respect to x. All right, so go ahead and try these. It is possible that there's not enough information on some of them. Okay, so give them a try, pause it, and then come back and I'm going to explain. Hopefully you paused. Here comes the explanation. So the integral from 1 to 4 is going to be 2. Or from 4 to 1 is going to be 2, because you would take So 4 is greater than 1, so you'd have to change the bounds, and then take the negative. So we change the bounds from 1 to 4, or 2, 1 to 4, and then take the negative of negative 2, that's positive 2. Okay. Part B, part B is 3. So we're going from negative 1 to 4 of f of x. We know what it is from negative 1 to 1, it's 5. And from 1 to 4 is negative 2. So 3 is our answer on that one. C, 2f of x, 3h of x. And we know the integral from negative 1 to 1 of f. And we know the integral from negative 1 to 1 of h. This turns out to be 31. We do 2 times f of x, which is 5, so that's 10, plus 3 times h of x, which is 21. So 21 plus 10 is 31. D, 0 to 1 of f of x. There's not enough information. Enough info. All right, we don't know enough, because if we're going from 0 to 1, we cannot assume that it's half of 5. The curve could be doing any number of things that would result in it not being half. Okay. From negative 1 to 4, f of x plus h of x. Again, not enough information here. We do know h from negative 1 to 1, but we don't know all the way to 4, although we can get f. So we could figure out what f was from negative 1 to 4, as we already did. That's 3, but we don't know enough information about h to answer that one. So that one is also not enough information. Okay. And I think that's where we're going to end this video. In the next video, we're going to talk about the average value of a function, and we're going to leave out a proof, which I'm sure you'll be happy about, and then we are going to talk about definite integrals using antiderivatives, right?